Hello, I hope you can hear me.
I can hear you. That's lovely.
Great. So my project is based on plasma surface modification of ultra-high molecular weight polyethylene and its effects on adhesion and wettability. This project is supervised by Professor Michael Wisdom, Professor Ian Hamilton, and Dr. Mark Hazard from DSM. Yep. So the aim of this project is to improve the mechanical performance of composites that incorporate Dyneema fibers as reinforcements, and the objectives include the chemical modification of surfaces using plasma treatment at different exposure times and different powers as well, to determine how the plasma treatment affects the wettability of these fibers, which is primarily studied using force tensiometry and drop shape analysis, and determining the adhesion of these fibers with thermosetting matrices such as epoxy matrix using single fiber testing, microbond testing route, and then finally testing the composite coupons to determine the ILSS and seeing how the plasma treatment affects the ILSS. And then we'll be looking in depth at the FE analysis to understand the fiber resin interface. So what plasma treatment does is when it interacts with the polyethylene, it basically breaks the carbon-to-carbon bonds in the main chain and also the pendant groups. And these are the sites where the functional groups that comes from the plasma jet stream attached to the surface. So as a result of plasma treatment, we can see that there is formation of carbon double bonds and attachment of oxygen at different wave numbers as seen by the FTIR data. We also did XPS to understand the percentage of oxygen content onto the surface as a result of plasma treatment. And we found that if we deconvolute the C1s peak from XPS data, we found that there was a 67% increase in the oxygen content as a result of plasma treatment. To understand how the plasma treatment enhances the wettability of these fibers, we did we used Owen's Vent model to understand the wettability, which essentially uses two different liquids, such as one with the polar component and one with the dispersive component. And then you find the contact angle of the drop that is being placed onto the surface. And what we found was that at 10% exposure time, at 10 seconds exposure time, both the total surface free energy and the dispersive component and the polar component increases. However, there's no appreciable change at higher exposure times. So this means that the surface becomes more polar as a result of plasma treatment. To understand adhesion and effects of plasma treatment on adhesion, we did single fiber testing, predominantly microbond testing, where a droplet of epoxy resin was cured onto the surface of single fiber and then pulled through a set of microvices to understand, to find the total force that is required to debond the droplet from the fiber. So once we have the maximum force for each sample, we would plot it against embedment length to determine the interfacial shear strength. We tested two different types of samples, aged samples and unaged samples. Aged samples were the samples that were tested 3 weeks after the plasma treatment, and unaged samples were the samples that were tested right away. And we know that plasma treatment is a temporary treatment. That is why we tested two different types of samples to incorporate the effect of fade away or hydrophobic recovery of the treatment. And we found that in both cases, the adhesion increases. However, the trends for aged and unaged samples is reversed. We also know that plasma treatment increases the surface roughness, and that could lead to the increase in the adhesion. However, it is to be noted that this testing method assumes that the stress is constant throughout the interface, and parameters such as fiber diameter variability can introduce variation or variability into the stress calculations. So finally, plasma treatment does increases chemical functionality. It does increase the IFSS on the samples, which is higher at lower exposure times, and for aged samples, and higher for unaged samples at higher exposure times. The total surface energy and its components increases, which is tended towards, which is basically affected more at the lower exposure times, and also the polar component is affected more than the dispersive component. The water contact angle reduces by 55%, which means that the surface becomes hydrophobic to moderately hydrophilic. I would like to acknowledge the supervisors, Professor Michael Wisdom, Professor Ian Hamilton, and Dr. Mark Hazard for their supervisory work, and BCI Lab support team for their support. Thank you very much.